Hello everyone, thank you for joining me today for this online version of the World Water Day event at Birmingham. My name is John Mackay. I work at the British Geological Survey and the title of my talk is Climate Change, Glacier Retreat and Water Security. I'm really interested in sort of three disciplines, and a lot of my work crosses those disciplines, which are glaciology, hydrology and hydrogeology as well. So my work kind of spans or is really focuses on water cycling in cold region environments. So the kind of environments where you get lots of snow and ice in the form of glaciers. And the head of my talk is warming water towers. So water towers is a term that we often use to describe mountain environments. So mountains receive a disproportionately large amount of water through precipitation processes, either through rainfall or snowfall, and they distribute that to downstream systems through runoff and subsurface processes. But the kinds of water towers that I'm interested in are the water towers that have glaciers in them. So glaciers have a really profound influence on the runoff regime of these mountain water towers. So they accumulate mass, they accumulate ice as snowfall during the cooler and often wetter times of year, and then they release it as meltwater in the warmer and often drier times of year, so arguably when water demand is highest. And because of that, they have a really profound influence on runoff characteristics of these systems. So this here is a sort of hypothetical set of hydrographs for three alpine river basins, but with differing levels of glacierization. So the black line here is a heavily glacierized river basin. It has this very smooth, very seasonal hydrograph. If we were to take that glacier away, you could end up with something more like this red hydrograph, which is much more stochastic, much more flashy, much more dependent on day-to-day rainfall runoff inputs. So the glacier has a really profound influence, and the reason for this seasonal cycle, of course, is because of the melt cycle. So you're getting melt during the warmer time of the year, and you get this really nice, smooth sort of hydrograph. And these glaciers, these water towers with glaciers on them can be found all over the world. So we've got the Himalaya, the Andes, we've got Alaska, Central Europe, Scandinavia. So they're a really important control on water availability in lots of parts of the world. In terms of the number of people that are reliant on these water sources, it depends really on which literature you actually look at. So some sources will say that you're talking of billions of people that are reliant on the water. Some will say it's more like millions. But if you were to take a sort of stab down the middle, you're talking about hundreds of millions of people that live in areas where glacier meltwater contributes a significant component of their water supply. So it really is they really are an important component of water availability. So how do we use meltwater? Well, meltwater provides energy security. So an example, this is the Tarbela Dam in Pakistan. This is the world's largest earth-filled dam. It generates about 5,000 megawatts of electricity through the hydroelectric power station that they've constructed in this dam. So it's a really major player in the overall energy availability of Pakistan. And it's fed by the Indus River. And the Indus River, of course, is fed by meltwater from the Himalaya and the Karakoram mountain ranges. So here we can see how meltwater from glaciers helps to provide energy security for Pakistan. Meltwater can also be important for providing food and food security and economic security as well. So as an example of that, this is the Chavimochic irrigation project in Peru. So this was a project that was initiated in the 1980s, and it aimed to transform about 70,000 hectares of what was essentially desert. It's an extremely dry, arid area on the coast of Peru, and they wanted to transform that into a land that could be cultivated, so it could be used for farming. And they did that by excavating this huge canal from the Rio Santa northwards along the coast. This canal could then be used for irrigation. But the Rio Santa, of course, is fed by meltwater, and it's fed by meltwater from the Cordillera Blanca. So here we can see how meltwater can provide food security and economic security for a country. Meltwater is also, can also be really important for the ecology of river basins, and particularly in river systems. So if we're looking at hydroecology, meltwater, it's been shown actually forms a really important, is a really important player in the sort of hydroecology of rivers. So these plots here are taken from a study led by a group at University of Birmingham. So they were looking at some meltwater-fed rivers in the French Pyrenees. And the first thing they did is they looked at physical and chemical properties of those rivers and related that to the overall meltwater contribution to those rivers. And that's what all these plots show here on these graphs. So on the x-axis, you've got meltwater contribution from 0 to 100%. And then on the y-axis, you've got various physical chemical properties. So you've got things like pH, suspended sediment concentration, conductivity, things like that. And you can see how the meltwater contribution has a clear control over some of these key properties. And of course, those properties also have a bearing on the hydroecology, so things that are living inside that river. So they went on then to look at different macroinvertebrate metrics of biodiversity and richness. And you can see here with the equivalent graphs, where we've got meltwater contribution again on the x-axis, you get these really interesting unimodal distributions for a lot of these different indices of biodiversity and richness. So this shows that there's kind of like a sort of happy medium where if you have a considerable amount of meltwater contribution, somewhere in the region of about 40%, that tends to result in a more diverse and rich macroinvertebrate ecosystem. So meltwater can also be really important ecologically. So the problem that we face now is that glaciers are retreating, and they're retreating rapidly, and this is a global, a truly global issue. So if we look at one of the latest analyses of glacier mass balance data, this was published in Nature last year. Just to take a quote from that, it says, present mass loss rates indicate that glaciers could almost disappear in some mountain ranges in this century. So this is one of the key figures from that study. And it shows you the cumulative specific mass change of glaciers around the world. Each of these lines refers to a different region from 1961 to 2021. And you can see almost all of them, except in fact all of them apart from one, are venturing into this negative zone. So it's indicating that they are retreating, they're losing mass. Just to pick a few metrics from there as well, they report that global glacier mass loss on average is probably around 335 gigatons per year. So that's between 2006 to 2016, so in one of the, a recent decade. And that equates, depending on which region you look at, you're talking about 0.5 to about 3% of the total ice volume. So it's not insignificant. It's actually a really big chunk of water and ice that's being lost every year. And of course, it's directly linked to rising global mean surface temperatures. And the implication for this, of course, is that we're seeing changes. In fact, now we're seeing changes, and in the future we're likely to see even more changes in global runoff, so runoff from these glacierized river basins. This is a figure that I've taken from, again, another recent study a couple of years ago, published in Nature Climate Change. They did a global analysis of glacier retreat and its implications for bulk meltwater inputs to river basins. And they actually took a glacier hydrological model and forced it into the future, up to the end of the 21st century, so all the way to 2100. And then they focused their analysis on a concept called peak water. So peak water is essentially the time, hopefully in the future, where you might expect water outputs from glacierized river basins to be maximum. So essentially what happens is as the climate warms, more of the glacier begins to melt, so more of the glacier surface area provides meltwater into the system, and you'd expect as it continues to warm and more of the glacier melts, that flows will gradually go up, so the amount of discharge it releases goes up. But then it gets to a point where as the glacier shrinks, and continues to melt, the size of the glacier then becomes the limiting factor on the amount of flow it can supply downstream. So then we'd expect to see the flow reduce. But the alarming thing about this analysis is that it showed that for over half the tested basins, so they tested basins all around the world, for over half of these, this peak water has actually already been reached. So this is a problem that we're going to face in the future, but it's also a problem that we're facing now. We're already seeing lasting effects. And that's really what my sort of, I guess, a lot of my motivation for what I do, for the work I do. I'm interested in this cascade of impacts from climate to glaciers shrinking, and then to impacts on water security, to society and to the environment. And I guess you could add on another bit there, which perhaps I should have done, which is adaptation. So then how do we adapt to these changes? And really that's kind of my motivation, and I'll be continuing to talk about that a bit more. So the way we do this is we use models. We use models of the climate to help us project how climate's going to change in the future. We use models of glaciers and hydrological models to then understand how glaciers respond and how water resources are going to change in the future. But it's tricky, and we're doing that at the moment, but there are lots of challenges that we face in doing that. So I want to spend the sort of second half of this talk talking about some of those challenges and talking a bit more about the research and some of the research challenges that we're facing now in terms of trying to complete this sort of puzzle and trying to understand how we go from climate change to water security, and then probably adaptation as well in the end, which I'll talk a little bit about. So the first challenge, I think, is that actually we need to look beyond the glacier. So what I mean by that is, if you look at a lot of studies that have been done in the past, there's a lot of focus on trying to understand how global glacier mass changes are going to play out in the future, so how glaciers are likely to shrink over the future. And then the impact that will have on bulk meltwater runoff inputs to the environment, to downstream systems. And all of that research is super useful, and it's provided us with some amazing insights into potentially how things could change in the future. But I think when you start getting down to local impacts and starting to think maybe more about adaptation strategies, we actually need to think about the wider hydrological cycle. How does meltwater propagate through the hydrological system? What stores does it end up in? Does it end up underground? Does it end up overground? And if we understand that, that's how we can start to build a picture of water security and potentially how we can adapt to those changes. So really we need to start thinking about developing models that really span across different hydrological boundaries. So I just want to spend a bit of time talking about that now. So obviously, working at the British Geological Survey, I'm quite interested in things underground, and groundwater in particular is one of the key components of the hydrological cycle that I'm particularly interested in. And there's definitely increasing interest in research in groundwater systems in glacierised river basins. And this is a really nice example of a recent piece of research that was done. This is published in Geophysical Research Letters. It's a group at the hydrogeology group at McGill University. And they focused their study on the Xolcus watershed in Peru. So this river system is fed by the Huaytopolana mountain range, which you can see here, a glaciarised mountain range. But they really wanted to look a bit more at the groundwater system downstream of this glaciarised basin. So they constructed a model that consisted of a glacier model that could simulate glacier mass balance and dynamics, a surface hydrology model, and importantly a groundwater model, so something that could simulate water underground. And by doing that, they were able to really sort of poke into how the system works and look at which are the key constituents of the water balance and water cycling in this system. The first thing they showed is that groundwater is a really, really important component of the water balance, particularly in the dry season. So if we look at this graph of river discharge in the Shulkus River, this blue section underneath indicates how much groundwater is contributing to that. And you can see during dry season flows, it's almost the only contributor to river discharge. So groundwater is really important for maintaining dry season flows. And they went on a little bit further and actually forced their model into the future. So they forced it all the way to the end of the 21st century, to 2100. And then they started looking at dry season fluxes in the model. So they showed that meltwater inputs, relatively stable from 1960, but then once we go into to 2020 and beyond, we can see meltwater inputs are drastically reducing and pretty much reducing to zero as the glacier recedes. But for groundwater, indicated by this orange line, so groundwater fluxes to the surface, we can see they're actually relatively stable. They do reduce slightly, and they attributed that to some other components of the water balance, such as evaporation. But generally speaking, the groundwater component is relatively stable. It's actually helping to buffer some of these changes in meltwater fluxes that we're seeing. So starting to look beyond the glacier and looking at other components of the system, it could really help us in terms of developing some of these adaptation strategies. There might be other components of the hydrosphere that we need to think about. And I myself have done quite a bit of work on this. So up until very recently, I was working in Iceland. This is the Geological glacier in southern Iceland. This is a glacier observatory that was set up by the British Geological Survey. And you can see this huge, expansive, almost like desert space in front of this glacierised mountain water tower system. And this is a sander. This is a floodplain, and it's made up of hundreds of meters of unconsolidated sediment and gravel and things that have all been kicked off this mountain system over the decades. And actually, it's a significant groundwater store. It's full of water. It's a huge, permeable, very, very high storage system. And this groundwater system readily interacts with meltwater runoff emanating from this glacierised mountain system. So as part of my research, I developed, along with my colleagues, an integrated model of not only glacier hydrology, so thinking about the mountain water tower system, but also this proglacial groundwater system. So I linked a distributed groundwater model to it. And this allowed us to really look at some of the water cycle components in really high detail. So we could look at things like how the water table fluctuates in that proglacial aquifer. And we could look at other fluxes, like recharge fluxes going into the aquifer and how those change over time. And we could also look at how fluxes emanate from the river into the groundwater system. So we were really interested in looking at the importance of the river as a source of recharge to the groundwater. So could the glacier meltwater that emanates into the river then actually be an important contributor to recharge to the groundwater system? And we actually found that it is quite significant. At certain times of the year, it is a significant input to this groundwater system. So there's some indication that this proglacial aquifer is actually dependent on the glacier. And then what we went on to do is test a series of different scenarios. So we put future climate scenarios through the model and tested to see how those recharge fluxes from the river into the groundwater changed. And we actually found that there was quite a high degree of variability between those scenarios. And it was all controlled by, the variability was a result of how much the glacier was retreating. And it wasn't that as the glacier retreated, you got less water going into the river. Actually, the amount of water in the river was about the same. It's just that it switched from glacier meltwater to rainfall runoff instead. But the reason that we saw differences across the scenarios was actually because if you look at a hydrograph, a river flow hydrograph emanating from a glacierised river basin, if you zoom right into that time series and get all the way down to a day, you'll find it has this diurnal cycle. So it has this diurnal melt cycle. River flows go up, as the day warms and the melt increases and melt ends up in the system, and then it goes back down again towards the end of the day and the cooler time of the day as melt gradually decreases. And we found that periodic rising and falling of river flows every day almost act like a pumping system. It would push water into this proglacial groundwater system. So if you lose that glacier, you lose that kind of pumping system, and therefore the amount of recharge that would get into the river actually reduced over time. So these are the kind of things that we need to start thinking about how the whole system behaves, and not just looking at one particular component. So this is a photo I took in November last year. This is in Peru. This is the study area of a new project that I'm now working on. This is quite a common sight you find if you're in the Peruvian Andes, if you're in the highlands. You'll see mountains, you'll see glaciers on top of those mountains, and then you see these quite lush green plains within the valleys of these mountains, often with alpacas because they're farmed in these areas. These are actually wetlands. They're huge water stores, locally known as bofedales. They store huge amounts of water, and they also store huge amounts of carbon, so they provide a number of ecosystem services. But in this project, we were really interested in looking beyond the glacier and looking at the whole hydrological cycle. And the bofedales, one of the things that we're going to focus on. So in this project, we're working in the Vilcanota Urubamba basin, which is in southern Peru. It's in the Cusco region of Peru. The project's called RAHU. It's being led by Imperial College, and we're working with the University of Birmingham, and then various institutes and universities, including UTEC and UNSAC in Peru. And the aim of this project is really to fulfill that flow diagram that I showed you, where we go from climate to glacier shrinkage to water security. And then also that little add-on as well. We really want to be able to come up with a model that can help us look at adaptation strategies as well for this region. So we're interested in glacier shrinkage and then going on to adaptation strategies. So at the moment we're developing that model framework, but actually what our focus has been on primarily, because we're still quite early on in this project, we're looking mainly at increasing the observation data that we have, because if you go to most mountain systems, there's almost no observation data. So very rarely do you find data on river flows or meteorological stations or anything like that. So we're really trying to build in some of that infrastructure to this region. So these are a couple of photos. So we hiked up to one of the glaciers there. This is Suyaporina. And we were on the glaciers. These are a couple of our colleagues who are helping us. And we drilled in ablation stakes on these glaciers. So these stakes allow us to measure how much the glacier is melting, so we can understand how much water might be emanating from these glaciers. We then came down onto the bofedales, and on these bofedales we installed a series of boreholes. These orange tubes here, you can see they're boreholes. So we'd drill those into the ground, and then this allows us to measure the water table, water storage within the bofedales. And to do that, we use these low-cost sensors. These are Arduinos, Arduino water level sensors. They were developed at Imperial College, and we've actually been putting them into boreholes into the bofedales so that we can continuously monitor how storage changes how storage is varying in these wetlands, in these bofedales over time. And then as we start to get a handle on how much glaciers are melting, how much meltwater flux is coming out, how these bofedales storages are changing, we can start to build up a picture of how water fluxes are propagating through the system and start looking beyond the glacier. And of course, all this observation data it's super important. If we're going to build models, we need observation data to back them up with, and this is a really important component and a challenge in itself, if you like, is building up that observation network. So I think the second big challenge we have in terms of thinking about glacier shrinkage and water security is dealing with uncertainty. So Any model that we use, whether it's a climate model or a hydrology model or whatever it is, of course they're not perfect. They've got lots of issues with them. And they're validated with observation data, which itself isn't perfect and is prone to errors. So whenever we make projections, whenever we want to talk about water security in the future, we have to accept that there's a certain degree of uncertainty associated with those projections. And some of the work that I've been doing has really been trying to deal with that uncertainty, trying to face it head on and start to try and understand and pick apart that uncertainty and where it comes from. So if we were going to ask the question, well, how will the runoff regime change in a glaciarized river basin over the 21st century? Well, the first question would be, well, presumably the climate's going to change, but it will change dependent on how we behave as humans, how many greenhouse gases we emit, or as we often talk about, how the representative concentration pathway, or RCP, will play out. And then when you think about which climate model do we use, there's not just one climate model, but there's multiple climate models out there. They're all parameterized and constructed in different ways, so they all give slightly different simulations. So there's an uncertainty about what each of those climate models is telling us. We might want to employ a sort of downscaling approach where we take climate projections and downscale them to a finer resolution so that they're compatible with our hydrology models. And then our glacier and hydrology model, there's lots of different models out there. We have to parameterize them, and often we don't have the observation data to do that. So there's some uncertainty associated with those. So you can see we have this whole cascade of uncertainty going through any given model framework. And really we need to think about this and try and quantify it as best we can. So I've done a bit of work on this myself, and this is, we're going back now to the Geological Glacier Observatory in Iceland, and we undertook a bunch of experiments looking at these different sources of uncertainty in this cascade. So we used 2 different representative concentration pathways. We used 14 different climate models. We used 10 different downscaling procedures, and we used over 300 different configurations of a glacier hydrological model. And we combined all of those to generate thousands of different future scenarios. And the useful thing about that is that we can actually start to put uncertainty bounds or confidence bounds around our predictions and our projections. So these are a series of projections we made for our catchment in Iceland. And these are all different metrics of river flow and how they'll change over time. So we've got things like mean monthly flows, or we've got metrics that look at really high flows, so if we're interested in, say, flood frequency in the future. We've got metrics looking at very low flows, so we might be interested in looking at drought. And we've got metrics that look at the timing of the system, so the sort of residence time, how quickly does it store and release water over time, and how is that going to change in the future. But the really nice thing, I think, about starting to do some analyses around the uncertainty and trying to deal with the uncertainty is to really sort of deconstruct them and start to try and understand where they stem from in that model chain. And that's what we did. We used a statistical approach to actually decompose these uncertainties. We used a statistical approach known as the analysis of variance, or ANOVA, which you might have heard of. And then for each of those metrics of future river flow, we actually quantified the contribution of each of those different model chain components, and that's what all these coloured bars indicate. But the really interesting thing we found is that they're by no means uniform across those different metrics. For example, if we were interested in low flows, perhaps we were interested in looking at drought severity in the future. This gold bar here is the one that dominates, and that one is associated with the way in which we represent glacier hydrology, so the way in which we represent water storage and release within a glacier. So that was a key source of uncertainty for that metric. But then if we look at different metrics, we see that other sources, perhaps the emission scenario or the climate model, are the key contributors to uncertainty. And this was really interesting, and it shows us that if we want to, again thinking back to that flow diagram going from climate to water security, if we wanted to undertake studies like that, we might want to tailor our modelling design so that it really hones in on on the key sources of uncertainty. If we want to look at drought, maybe we need to think more about the glacier hydrology than maybe we do about the different climate models. That can really help us sort of focus in and try and generate more robust projections. So the final challenge is maybe a little bit more blue skies, but it's certainly the direction that research is going in now. Increasingly, we're seeing studies that are not just focusing on one catchment, perhaps not even focusing on one region, but they're looking at the entire globe. So they're looking at all the glaciers, all of the river basins around the world. And this is a big challenge. So can we make model predictions for everywhere? And I guess the answer to that is, well, yes, we can. There are lots of large-scale, often open-source models now. For example, for glacier evolution, if we're interested in simulating glacier dynamics and glacier mass balance, there's models like OGGM, which is the Open Global Glacier Model. There's PyGEM, which is another sort of Python glacier evolution model, and GlowGEM as well. It's been used in some studies recently. So the technology is there to start making these, start doing these studies and to start looking at global variations. And the really nice thing about these is that they really do show some fascinating results in terms of different responses across regions and across the globe, and you really get a nice picture of how different systems behave and really the variability between those, and it's really quite insightful. But one of the things they're still lacking, they're still suffering from that challenge one, going beyond the glacier. So a lot of these studies that have used these kind of models, for example, have tended to be quite glacier-centric. They've focused on getting the glacier right, and then maybe not accounting for the wider hydrology, which is not a criticism, by the way, because it's totally fit for purpose. But I think if we want to be able to make global projections that are really relevant to water security issues, then we might want to think about going beyond the glacier again. So this is my last slide, and it's more of a plug than anything else on a new project that I'm working on. It's a project called HydroJoules. So JOULES is a land surface model. It's the joint UK land environment simulator. And HydroJoules is a sort of cooperative project to develop the next generation of JOULES, so to really try and improve the code. And this is, we're working with the UK Centre of Ecology and Hydrology and NCAS, the National Centre for Atmospheric Science. And one of the aims of the project, there are lots of different aims of this project, but one of them is to develop a code that is more generally applicable to large-scale, global-scale studies. So one of the things that I'm doing on this particular project is trying to improve the representation of glaciers in it. So actually, this model already has a very sophisticated representation of hydrology, although we are trying to improve that as well. But it doesn't have much in the way of representation of glaciers at the moment, and that can certainly be improved. So that's currently what I'm working on. So in terms of large-scale global projections that are applicable to water resource issues, I'm hoping this project could be really pivotal in kind of pushing that forward. So this is kind of a watch this space slide, and yeah, see what happens. So please do go and take a look at this if you get a chance. Okay, thank you for listening to this online presentation. If you have any questions, then please feel free to contact me. I'm sure there'll be some kind of contact info down below, but if you can't find me, just type in my name and BGS and you'll find my profile online. Thank you very much.